The topic of this screencast is the conceptual and qualitative physics of fluorescence. This screencast will intentionally steer away from the mathematical details. It will avoid equations when possible. It will avoid all derivations. Those will be treated later. And so it's going to emphasize the qualitative physics and the concepts behind it. We'll see that dipoles are tremendously important. We'll also see that something called the Jablonski diagram is essentially it's a simple schematic representation of the important concepts. So it's sort of a unifying schematic focal point that you can refer to review, understand a tremendous amount about fluorescence. So we'll come back to the Jablonski diagram momentarily. This presentation is based on the May 4, 2016 version of the PowerPoint. So let's jump into it. So before we go forward with fluorescence, we're going to step back. And so we've spent a significant amount of time talking about charge distributions in molecules and the definition of the dipole moment and the interaction of light with molecules and the necessity for there to be a change in dipole moment for light to be absorbed by a molecule. Now, you will see in fluorescence that this is important in many, many ways. For one thing, the starting point for fluorescence phenomenon, the starting point for fluorescence as it's typically used in the laboratory and in biological sciences is absorption of a photon by a molecule to go into an excited electronic state. So basically, fluorescence is under most experimental conditions driven by light absorption. I did point out in one of the previous screencasts that that is not the only form of fluorescence. Infrared fluorescence all kinds of fluorescence can happen spontaneously. To what extent they do depends on to what the occupancy of higher energy states that are able to then emit photons as they decay to lower energy states. Of course, the energy of a photon, the quantized energy, is linearly proportional to the frequency. So higher frequency light, higher energy photons, lower frequency light, lower energy photons. In the infrared region, which has higher wavelength and lower frequency than the visible, the photons have somewhat lower energy. Therefore, the electronic transitions being stimulated by those photons or the photons being emitted as things decay to the ground state have lower energy. In the infrared, although the most common, as we'll see shortly, this will become important in fluorescence, the lowest energy state is always has the highest relative occupancy. We will look at that via the Boltzmann relationship shortly, because that is important to fluorescence. So the higher the energy level, it is always true at thermal equilibrium, the lower relative population of that state. But the extent of the population will depend on the energy levels, the energy differences. In the infrared, those energy differences are small enough that although the overwhelming majority of the molecules will be in the vibrational ground state, thermal energy is enough to have some of them, some molecules in excited vibrational states. And so thermal energy is closer at room temperature, the temperature where organisms generally live. Those temperatures produce significant, still small, but significant population of vibrational excited states, and they can spontaneously emit photons as they decay to the vibrational ground state. So we'll see like a whole bunch of things about, optical physics and molecular physics influence what we see in fluorescence. And so it's a very, in addition to being an incredibly useful phenomenon practically, it's a good one to focus on understanding because it integrates a lot of different things in molecular and optical physics. So one of those important things is that for a light wave to induce a transition in a molecule, first of all, the quantized energy of the photon at whatever frequency of light you're using has to match the energy difference of the transition. I'm sorry, the energy difference between the molecular quantum states involved, right? So this is totally key, right? That the energy, the photon energy, which is linearly proportional to frequency, has to match the difference in the energy of the molecular quantum states. So that's a necessary condition. The second necessary condition that affects the efficiency. These things have to match for it to be possible for there to be an absorption. The efficiency of the absorption is dependent on the change in the molecular dipole moment. And in particular, the probability of the transition scales with the square of the dot product of the electric field, with the change in the dipole moment of the molecule going from the ground state to the excited state in question. And so that has an important implication, right? That means this term, the transition dipole moment, the change in the dipole moment in the course of the the transition between the molecular quantum states has to change the dipole moment magnitude for there to be absorption of light, for light to be able to do work and drive the transition. So during the transitions driven by light, there has to be a change in the molecular dipole moment. That's why we spent a lot of time defining exactly what the molecular dipole moment is. The transition dipole moment vector is going to be the difference between the dipole if we're looking at a transition to quantum state 1 from quantum state 0, the transition dipole moment is basically the difference between it is slightly more complicated than this, as we've looked at earlier, but it is reasonably described as the difference between the dipole moment in that quantum state 1 minus the dipole moment in the quantum state 0. Now, importantly, this has a magnitude. If the magnitude is 0, the dot product up here will be 0. The probability of a light-induced transition will be 0. So the magnitude of this is quite important. But note also this is a vectorial quantity. It has a direction. When we get to fluorescence anisotropy, that will also be tremendously important. So we've been through all of this stuff before, but it is really the starting point for fluorescence, which is why I wanted to review it. So let's move on. Now, when a molecule goes between two different electronic states, right? Electronic states describe the spatial distribution of the electrons in a molecule. You can use quantum mechanical techniques of various kinds to describe those quantum states quantitatively. In the end, solving the full quantum mechanical wave function for the atom, for the molecule, right? You have to solve the full quantum mechanical wave function for the molecular system. That would be the best way to describe the quantum states. In practice, those calculations are extremely difficult, and so certain approximations are known. You've been exposed at one point or another, I'm sure, to the molecular orbital calculation, the different kinds of there are different ways of doing this, and again, most of them are sort of approximate ways to get a reasonably accurate, if approximate solution to the quantum mechanical wave equations. So the net result is that these molecular orbital calculations will approximate the quantum mechanical wave functions in the molecule under different states. And one set of terms that you might have heard before are the LUMO, or the HOMO, the highest occupied molecular orbital, and LUMO, lowest unoccupied molecular orbital. And so in the end, when you solve the quantum mechanical wave function for a complicated molecule, you will get a number of different basically molecular wave functions. The Pauli principle will tell you sort of fill those up with pairs of electrons, and the Boltzmann weighting and other things will tell you that in general, the electrons will go into the lowest energy wave function first, and then they will go into the next highest energy wave function, the next highest energy. So pairs of electrons will fill the orbitals in the order of their energy, with the lowest energy orbitals being filled first, and then progressively higher energy orbitals being filled. So in the ground state of the electronic distribution for a molecule, of the electron configuration in a molecule, you will have some highest occupied molecular orbital with complete occupancy of all the lower energy molecular orbitals. So typically then electronic transitions, well, always electronic transitions will take place between different electronic molecular orbital states. In the electronic ground state, typically, again, all the lowest energy molecular orbitals will be filled in order. And the lowest energy electronic transition will typically be then into the lowest energy excited state or unoccupied molecular orbital state. And so that's where these terms come from. HOMO, highest occupied molecular orbital. That would be sort of, what's filled, the highest energy orbital filled in the ground state. The LUMO, the lowest unoccupied molecular orbital. That's the molecular orbital with the lowest energy, and that therefore has that's the unoccupied orbital with the lowest energy, and therefore the lowest energy electronic transition will be from basically the HOMO, highest occupied molecular orbital, to the LUMO, the lowest unoccupied. So, of course, transitions can happen into higher energy unoccupied molecular orbitals, but the lowest energy transition that can happen out of the electronic ground state will be into the lowest unoccupied molecular orbital. So that's going to be the easiest one to observe energetically, and that's most frequently that is it's what you will most frequently be observing in optical absorption spectra. So the starting point for fluorescence is going to be an optical absorption, and in meaning a photon being absorbed and changing the molecule, in promoting an electron from a currently occupied orbital to a currently unoccupied orbital. And so again, the lowest energy optical transition or electronic transition is going to be from the HOMO to the LUMO orbital. These can be approximated by quantum mechanical calculations. They're an example of such calculations shown here. Now, what's shown in these diagrams, this might be slightly confusing. Red and blue is often meant to denote electronic, well, whatever, represent electronic potential. In this case, that's not what's being represented in these diagrams, which I took off the internet with due attribution here. Red and blue are representing positive and negative signs of the quantum mechanical wave function. Now, the electron distribution in the end will be given, the probability of finding an electron at a given point is going to be given by the square of these quantum mechanical wave functions. So basically, anywhere where there's red or blue here, you will be finding the electrons more frequently than the places where there is not. And so this is an example of a representative molecular orbital calculation on a complicated molecule of the kind that it might have a fluorescence emission. We'll talk more about that in a bit. But you can see that in the highest occupied molecular orbital, there is a characteristic distribution of basically the electron density. These things, the square of these things more or less will scale with where the electrons are going to be found. Now, when you go to the lowest unoccupied molecular orbital, you see there's a totally different distribution for the electron probability. So what does this mean? This means the electrons move around. The electrons will move around from being like largely, most probably in this region of the molecule, in the highest occupied molecular orbital, to being primarily in this region of the molecule, in the lowest unoccupied molecular orbital. And so what happens when have the nuclei changed their position? No, there's something called the Frank Condon principle that we'll come to shortly, saying that the nuclei in general are not going to change their position significantly. But the electrons, right? So the nuclei have not changed their spatial distribution significantly. The electrons have changed their distribution significantly. Of course, the nuclei carry the positive charge. The electrons carry the negative charge. If the electrons now have a different preferred spatial distribution, but the nuclei do not, it means the dipole moment will have changed, right? If the negative charge shifts around and the positive charge does not, the dipole moment will change. So this shows that in the course of an electronic transition, again, there can be rearrangement in the electron. Typically, there's going to be some rearrangement in the electron density distribution. Here's an example where there's quite a significant shift in the electron density distribution towards one end of the molecule. Since that happens with the nuclei staying in their roughly the same equilibrium positions relative to the center of mass, that means there'll be a shift basically in the dipole moment. The charge distribution has changed, the dipole moment will change. And so, you can infer that this will be a so-called allowed electronic transition, that it will be possible for light of the appropriate wavelength, right, light with a photon matching the energy of this difference between the two molecular orbitals, will be able to excite that transition because, of course, well, first of all, light of the right, you will need light of the right wavelength or frequency to match the energy difference. That is a requirement. But it is also for the light to transfer energy to the molecule. It is also a requirement. Well, for it to transfer energy via the electric field is a requirement for the electric field to be able to do work. That will depend on there being a change in the dipole moment of the molecule, as we showed earlier. These simple, well, relatively, these representative molecular orbital calculations show that in this case there's going to be quite a change in the electron distribution, and therefore there will be a change in the dipole moment. The dipole moment is the volume integral of the first spatial moment of the electron density, right? So it's the integral of the position. It's integrated over every position in a molecule, right? It's integrating over the whole volume of the molecule. At every position, you take the vector to that position, you weight it by the electron density, and then you sum that over the volume. So it is a electron density weighted integration over the positions in the atom, right? When the electron density distribution changes, this first moment of the electron density distribution changes, the dipole moment changes. There will be a non-zero transition dipole moment. As we said before, it will have a magnitude. If the magnitude is non-zero, as it clearly will be for a transition of this kind, you can get an the electric field of light can induce a transition, and you can get an electronic absorption. In the course of that absorption, the dipole moment will change. So we've sort of been through all this before. We want it to be concrete because it is incredibly important in fluorescence. So what are we looking at in fluorescence? So some typical examples of both just the phenomenon, some typical examples of both the phenomenon of fluorescence and let's say the most basic sort of physics of fluorescence are shown here in figures taken out of the Lakowitz book. So these are different different molecules that fluoresce in the visible region of the electromagnetic spectrum, as they all end up having conjugated ring systems. Again, the reason that visible fluorophores often have conjugated ring systems is because compared to molecules with single bonds or non-conjugated rings, the lowest lying excited energy states are closer in energy, and therefore you can transitions between them can be promoted by light of lower energy or higher wavelength. And so the molecular orbitals that tend to match the energy the quantized energy of light in the visible region tends to match that of between the ground state and first excited state orbitals in conjugated ring systems. So that's most visible fluorophores have conjugated ring systems. So in the end, we have these, somewhat complicated organic molecules, but they glow. And fluorescence is all about this special kind of glowing. You can see you have these molecules now, depending on their atomic structure. Of course, their molecular structure. Their molecular structure will, of course, influence the quantum mechanical electronic energy levels. As the structure changes, the energy levels change. The separation between them changes. With different molecules, we can get just about any color. And there's a whole field of research in actually computational quantum mechanics that tries to sort of simulate this, and it's quite successful. So you can sort of design fluorescent molecules, and that's been an important technological activity for the chemistry and biology communities for the last half century or so. So this over here describes just the phenomenon of fluorescence. This describes the most basic physics of it. Okay, so what is it that we have over here? So basically these are two kinds of spectra just put on the same axis. The left portion here is an absorption spectrum. The right portion here is a fluorescence emission spectrum. Sorry. You can see that they actually overlap a bit at the midpoint, and that they roughly have sort of a mirror image profile around this midpoint. And so this is showing the absorption spectrum of this molecule. Again, with a conjugated ring system, this is showing the emission spectrum of this molecule. Where is this in the electromagnetic spectrum? Well, 350 is generally considered the boundary of the UV compared to visible. And so the absorbance here is sort of at the edge of the visible UV junction, and the emission is in the visible region, right? So now the energy of the emission, right? If it's higher wavelength, it's lower energy. The energy of the emission is lower than the energy of the excitation. That is always going to be true for fluorescence. Of course, by conservation of energy, it should not be higher. One question is, why is it lower? We're going to get to that momentarily. So this is the most primitive form, in a sense, of a Jablonski diagram. This is showing, supposed to be schematizing the relevant molecular quantum states. The large energy differences are between electronic states. So this is supposed to be the electronic ground state. This is now a manifold of different states in the electronic excited state. So these are all in the electronic excited state. This is the ground state. This is now representing a manifold in the electronic ground state. So what are these manifolds? These manifolds are the vibrational states of the molecule. So in the electronic ground state, you can have different vibrational quantum states. The selection rules for absorption of light based on work being done by the electric field component allow for therefore to be simultaneous changes in electronic state and vibrational state. And sometimes it is stated as during an electrically driven transition by an electromagnetic wave, both the electric and vibrational quantum numbers of the electron can change. Okay, and so what you have here is you have a vibrational manifold in the ground state, and you have a vibrational manifold in the excited state. The selection rules, right, which depend on having a match between the frequency of light and the energy of the transition, and depend on the change in the magnitude of the dipole moment. The selection rules allow, and when you get into the quantum mechanics, there are other, sort of somewhat more subtle requirements. But the selection rules allow for a simultaneous transition to a higher electronic state and a different vibrational quantum state. The efficiency of the transitions to different states is not equal, but so there's not an equal probability of going into each one of these vibrational states in the electronic first excited state. But transitions into many of them are allowed to some extent. And again, that's sort of a quantum mechanical phenomenon that we're not going to go into in detail, but we'll just say that in general, right, what we see here now in the absorption spectrum, right, the most intense region of the absorption spectrum is the highest wavelength, lowest energy. So in general, it is more probable to go into the lower energy vibrational states than the higher energy vibrational states. As you get to higher and higher energy vibrational states, there is a drop-off in the probability of that transition being induced, and therefore a lower magnitude of absorbance. So in general, you have the strongest absorptions at the lowest energy, highest wavelength end, and then the strength of and that reflects transitions into the lowest energy vibrational state. And then as you go to higher energy vibrational states, there is a lower frequency, a lower probability of the transition being reduced, and therefore a lesser amount of light absorbed. So the Jablonski diagram schematizes the relevant molecular energy states. That's the first important content of it. There's an electronic state. Basically, it is an energy. There's an energy axis. The vertical axis here is energy, and so we can position in the energy axis the electronic ground state, and then the different vibrational substates in the electronic ground state, and then the first electronic excited state and the different vibrational substates in the first electronic excited state. There's actually something slightly unusual about the fluorescence properties of this molecule, which I will not go into detail. Let's not worry about it. But the one thing that is noteworthy, that is sort of apparent here, is that there is a rough, as I said before, mirror, as Lackowitz describes, there's a rough mirror image symmetry between the absorption spectrum and the emission spectrum. Right? What the emission spectrum reflects is the decay of the molecule from the electronic excited state to the electronic ground state. In the same rules, that the way that the selection rules for the absorption allow a transition from one electronic state, allow a simultaneous transition between different electronic and vibrational states, it is also true that during the fluorescence decay process, which is essentially a photon being emitted to remove the electronic excitation energy, during the fluorescence decay process, you can change to a lower electronic state. And you can simultaneously change to a different vibrational state. Now, in general, at thermal temperatures, in general, there's relatively low occupancy of the vibrational excited states. We'll come back to that later on, but there can be some occupancy of the vibrational excited states. But the implications of that, distribution of vibrational quantum states at thermal temperatures is going to be addressed in subsequent slides. For the moment, let's just focus on, sort of the most basic features of this. You go from the vibrational ground state and the electronic ground state to the electronic excited state into one of a set of different vibrational modes. This is called a vibrational manifold, the sort of set of different vibrational states. In general, going to the higher order vibrational states is less probable for quantum mechanical reasons, and therefore the absorption intensity declines because the probability of a transition into the higher energy vibrational quantum state goes down as the energy of that quantum state goes up, and so therefore the more energetic, right, to go to a higher energy vibrational state, you need to have a more energetic photon. The more energetic photons are at lower wavelength. As you go to lower wavelength, the probability of the absorption goes down, and so the spectrum tends to fall off. In the emission spectrum, you see sort of exactly the opposite. You see the strongest emission tends to be at the lowest wavelength or the highest energy, and then the probability of the absorption or the probability of the transition, the strength of the emission tails off as you go to higher energy. So, but there is rough mirror image symmetry, and what that means is there is roughly the same separation in the energy of the vibrational, there is roughly the same separation in energy between these peaks in the fluorescence emission spectrum as in the fluorescence absorption spectrum. What that reflects is that the vibrational energy states are pretty much the same in the electronic excited state or in the electronic ground state. And so that's something called the Franck-Condon principle. The Franck-Condon principle says the vibrational states don't change much when you go from the electronic ground to the electronic excited state because they're determined mostly by the nuclear positions, and the nuclear positions don't change much. As we saw in the preceding slide, when you go to the electronic excited state, the electrons are moving around a lot. That movement has to happen for there to be an absorption of light because you need to change the dipole moment. The nuclei don't move much because the nuclei are going to be the major determinant of the vibrational energies. The vibrational manifold, as it's called in the electronic state, tends to be the same. There tends to be the same energetic separation between vibrational levels in the electronic ground state as there is in the electronic excited state. That's the Franck-Condon principle. Again, it's mostly having to do with the nuclear positions not changing much during the electronic transition. If the vibrational manifolds are the same, well, again, the probability of going to higher order vibrational states declines as the energy of those states declines, right? So there's this fall off going in this direction in the absorption spectrum. The probability of decaying into a higher order vibrational state also declines as the energy of the vibrational state increases, right? And so the most probable decay is into the vibrational ground state, and then there's a somewhat less probable decay as the energy of the vibrational state increases. And so that's nicely schematized here. The red, I would have colored this differently, but what Lachowicz did is the red transition is the lowest energy transition. That is going to from the electronic ground state. I'm sorry, from the vibrational ground state in the electronic ground state to the vibrational ground state up here, and then what he has schematized for rather complicated reasons. I would not have picked this molecule as my principal example, but I guess it's the spectrum that he had handy. For rather complicated reasons, he's looking at a transition where it's occurring primarily from a vibrational, from a non-ground vibrational state. But anyway, the lowest energy, highest wavelength transition is into the most excited vibrational state depicted here, right? And so that's this transition. As you decay down into progressively lower energy vibrational states, you basically, the molecule is throwing off more energy in the photon. Therefore, the energy of the photon is getting higher. And when you come down to the vibrational ground state, then you have a higher energy, lower wavelength photon. So this is sort of the basic. These are the most basic features of fluorescence and of the Jablonski diagram. So hopefully we begin to see important properties of the qualitative physics of fluorescence, and we can see how the Jablonski diagram is a useful way to organize our understanding of this conceptually and understand a bit about a bit about it quantitatively. Okay, now just to pause over here for one moment, I will just point out that Lachowicz has a mistake over here. Wave number, of course, is reciprocal of wavelength, so wave number is proportional to frequency. Frequency is inversely proportional to wavelength. Wave number is inversely proportional to wavelength. Therefore, frequency and wave number are proportional to one another. So in this depiction, higher energy is up here, lower energy is down there. I'm not sure exactly what Lachowicz was thinking here. Well, I think he wasn't paying it very close attention. The bottom line is the absorption has to be at lower energy than the emission. He has mislabeled these things. In this decay depiction, right? This is higher energy. This is lower, right? Higher wave number, lower wavelength. This is the absorption spectrum. This is the emission spectrum, and he's just screwed that up. Wavelengths are shown for convenience. I don't know what exactly he did here. One way or another, there's something wrong. He either labeled a wavelength axis wave number, but I'm not, if I look at the numbers, I don't think that's what he did. I think he showed wave numbers and didn't think about it and then basically mislabeled these things. Or he was intending to do that. What did he do here? Oh, I'm sorry. What he has done, sorry. What he has done is so confusing that I became slightly confused. So he actually has a wavelength scale up here, and so this is sort of a linearly, yeah. Actually, he has a scale that increases with wavelength going in this direction, and therefore decreases in wave number going in this direction. I'm sorry. So the labels are correct, but I'm sorry. The labels of these peaks are correct. But he has chosen to plot these axes in a weird way. So he has a linear scale in wave number down here. He's shown the corresponding scale in wavelength up here. And he has it such that low wavelength, high energy is at the left, and high wavelength, low energy is at the right. So this is actually sort of the wave numbers, although it's a linear scale in wave numbers, I guess, it's going, the wave numbers are going down from left to right. Anyway, well, so don't be confused by that. It confused me momentarily. But anyway, the point is the same. This is another fluorophore where you can see the mirror image. You can see this so-called, mirror image rule, which means that the absorption spectrum roughly is the mirror image of the emission spectrum. That's because the vibrational manifold is roughly the same in the first electronic excited state as it is in the electronic ground state, and then the allowed transitions, which occur between where simultaneously you change electronic state and vibrational state. When you think about how that all adds together, because the separation between the vibrational states is the same, that will produce this rough mirror image symmetry. Okay. And so this is just to remind you that what's going on in those vibrational states comes from the normal modes of the molecules. And so what we have in here, right, so this is now calibrated in wave numbers. Once again, the wave numbers are going down in this direction. So that means frequency is going down. That means energy is going down. That means the higher energy part of the spectrum is down here, the lower energy here. But remember, the visible spectrum is at still, right? So this is wave number is going up this way. Frequency is going, sorry, wave number is going up in this direction. This, yeah, anyway, wave number is going up in this direction, right? And so that's the positive. Greater wave numbers are in that direction. That means greater frequency is in that direction. That means greater energy is in this direction. Remember, visible region of the spectrum is down here yet further, so yet higher energy. So these vibrations are basically small energy differences compared to the energy difference of the visible photon. And what you're seeing then in that vibrational manifold are the possibility of going into, right? These are all different vibrational modes. They reflect putting energy into different simple harmonic motions of the atomic nuclei. They are all at lower energy and have lower energy separations between them than you would in the visible region of the spectrum. And so you get, but there are many different, right, normal modes that you can observe in the infrared spectrum. That means all of these different normal modes involve changes in the dipole moment during the trajectory of the normal mode. And so this is explaining why you have this manifold of different vibrational states, right? So you aren't necessarily going into the higher vibrational level of a given normal mode, but you have many different vibrational normal modes. And so as you go from the ground state to the electronic excited state, you can again change both the electronic quantum number, change the electronic quantum state and the vibrational quantum state. There are many different vibrational quantum states, and so the complexity of the fine structure in this spectrum reflects those many different vibrational quantum states. There are, computational principles and quantum mechanical principles that allow you to see that transition into some of these vibrational quantum states will be more likely than into others. There's sort of extensions of the Frank-Condon principle that quantitatively explain that. They're rather complicated to wrap your mind around, so I'm not going to go into them. Let's just say that in just focus on the simple point. In either the ground state or the electronic excited state, you have roughly the same vibrational manifolds. There are different normal modes. There are a whole bunch of different modes. All of those normal modes have lower energies separating them. The quantization of the energy in those normal modes is lower. They absorb in the infrared spectrum. That means they have lower energy differences between them than the electronic transitions. So the largest contributor to the energy, of course, is the electronic transitions, and then the transitions between different vibrational quantum states are lower in magnitude, and that's why you get this smaller separation between the different vibrational states. These can all, right, from the vibrational ground state of this molecule, the different vibrational energy levels can all reflect different normal modes, right? So this might be the first excited state of one normal mode, this might be the first excited state of another normal mode. The vibrational manifold is going to be the same in the ground or excited states. And so you will end up with the mirror symmetry. But there are quantum mechanical principles that actually have some classical analogs that make some of these simultaneous electronic and vibrational transitions more likely than others. And in general, when you're going to, as the energy of the vibrational quantum state gets higher, there's a lower probability. And so in general, the absorption drops off as you go to higher energy. It's less likely you're going to go to a vibrational quantum state the higher in energy that it is. So, and again, this is all sort of generally captured by the term Frank-Condon principle. The simplest explanation of that, again, is that the vibrational manifold doesn't change much in when the electronic quantum state changes, and therefore the vibrational manifolds are very similar. More advanced formulations of the Frank-Condon principle actually explain this fall-off in absorption probability and intensity with the energy of the vibrational quantum state. We're not going to go into those. Okay, so now we come back to the Jablonski diagram, and hopefully we already have a basic idea of what this means. And so this is a slightly more complicated version of it, and then this is a yet more complicated version. So I'm going to step through all this stuff in detail, but let's just summarize at the moment what's represented here. The Jablonski diagram represents the energy levels of the relevant molecular quantum states, right? Both electronic, the big gap, and vibrational. In this case now, and so you can have many different sort of fine formulations of this. This one is, it's the same kind of energy axis, the same kind of schematic diagram of molecular quantum states, but it's emphasizing different features than the last one. In this one, we have the electronic ground state, the vibrational manifold in the electronic ground state. We have the first electronic excited state, the second electronic excited state. And then we also have something called intersystem crossing. I'm going to step through all of this. I'm not going to spend a lot of time on any of it, but I will step through all of it at least quickly. But anyway, so the Jablonski diagram captures the energy levels of the relevant molecular quantum states. It can also capture the solvent interaction energy with the longer-lived molecular quantum states, and that's what's described down here in this solvent relaxation effect. And then it can describe processes that kinetically compete with fluorescence to remove energy from the molecule and thereby control quantum yield. But it does not describe the relative rates of these processes, right? So when fluorescence happens, a photon is emitted. The photon energy is exactly equal to the energy separating the excited molecular quantum state from the ground state, right? So when the photon is absorbed, the electron goes into a higher energy molecular orbital. We'll talk about internal conversion and solvent relaxation shortly, but the bottom line is at thermal temperatures, essentially the molecule rapidly goes into the ground vibrational state in a relaxed energy state in terms of solvent interactions. And these basically shake off some of the energy of absorption, right? And so, right, this is why the energy of a fluorescence emission is lower than the energy of the absorption. Some energy is shaken off before the photon is released. And then the fluorescence property involves releasing the photon. Again, at thermal temperatures, generally, the vast majority of molecules are in the vibrational ground state. So that's the state from which most of them will emit photons. If the photon is emitted from the vibrational ground state, the molecule can actually go into the photon. When the photon is emitted, it can go into excited vibrational states. That's what we saw before with the mirror image rule. So that process, the molecular states underlying the mirror image rule are schematized up here. What they've done down here is they've removed that vibrational manifold to just simplify things and focus conceptually on something else. What's focused here, they're just showing the decay from the first electronic excited state into the electronic ground state. And so the energy of the photon has to match that energy difference. And so that's the fluorescent emission. The rate of that fluorescent emission is represented by a variable here. This variable gamma will be used to represent the rate of the fluorescence emission. So the diagram is showing that has a characteristic rate. It is not, however, quantifying that rate. So what's shown here are the different pathways to remove the excitation. So the energy, the excited state energy can be released in the form of the photon, but then there are also collisional quenching processes. There are various non-radiative paths to shake off the energy. Basically, collisions in the solution can end up removing the excitation energy. So the energy in the electronic excitation can basically just be shaken off into the kinetic energy of the solvent. And that will occur with some rate and at some frequency. And then a process called collisional quenching. We'll talk about this in a bit. The collisional quencher can come in and actually, the quencher can then remove the excitation energy, right? Energy is conserved. The energy of the electron, right? The electron is promoted to a higher energy state. The energy stored in that electron in the higher energy state has to go somewhere. It can be emitted as fluorescence. It can be shaken off into thermal motions in the solvent, so-called non-radiative decays. One special form of non-radiative decay is something called collisional quenching, which actually involves the electron, as we'll see. In collisional quenching, typically the electron is actually moving away. Right now that the energy has gone to a higher energy, the electron has gone to a higher energy state, and ends up being easier to move it off into another molecule or an atom. That's typically what's happening in this process called collisional quenching. We'll talk about that in a bit. And then another way to remove the energy is something called FRET, fluorescence resonance energy transfer. And so we'll also talk about that in some detail. But the bottom line is that there are all these possible ways of removing the energy from the excited state. Effectively, the other pathways for removing the excited state energy compete with fluorescence. So in the end, the efficiency of fluorescence will depend on the relative rate of the fluorescent decay process compared to all of these other rates. All the other rates describing the other processes that can remove the electronic excitation by a process other than fluorescence. Okay, so the Jablonski diagram, again, is showing the relevant molecular energy levels. You can sort of formulate the diagram slightly differently to focus on different specific features of the process. It will also schematize the solvent interaction energy. That's shown here. We'll talk about this more in a bit, but basically, of course, for an electronic absorption to take place, the dipole moment has to change. What happens when the dipole moment changes, of course, in a polar solvent, the solvent has dipole moments. The dipole moments in the solvent are free to move around. Once you go to the electronic excited state and you have a bigger dipole moment, or maybe a smaller dipole moment, but once in the course of this electronic transition, the dipole moment had to change. It had to change because otherwise light would not be absorbed. The fact that light was absorbed means the dipole moment changes. So the solvent was equilibrated with some dipole moment down there, but now there's a new dipole moment. And so now the solvent will equilibrate with that new dipole moment. And that process is called solvent relaxation, right? And in general, systems will go to their lower energy states. So the dipoles in the solvent will rearrange so as to lower their energy of interaction with the now dipole of different magnitude in the excited state. A lowering of the excited state energy to solvent reorganization is called solvent relaxation. Okay, and so you can also schematize in the Jablonski diagram the solvent interaction energy with the longer-lived molecular quantum states. And so again, the Jablonski diagram captures the energy levels of the relevant molecular quantum states, the solvent interaction energy with the longer-lived molecular quantum states. Could capture it with whatever molecular quantum state, but the longer-lived ones are the most important to the fluorescence process. It can capture all the different processes that kinetically compete with fluorescence to remove energy from the molecule, but note it is not directly showing the rates of those processes, even the relative rates, right? It's just showing that these processes all move the molecular quantum energy from this level down to that level. It doesn't say anything about their relative rates. But their relative rates are quite important. Here's some of those. One of those rates is well, anyway, we could write in the rates here, but note the diagram is not in and of itself showing the rates, right? So these rates can move around. The Jablonski diagram will look the same. Here, the rate of this solvent relaxation process, this is indicated as 10 to the minus 10 seconds. So the time scale of fluorescence is quite important. The time scale of an optical absorption event is roughly the time it takes one wave. Well, it's roughly the time it takes one wave to pass one point in space. So this is basically the frequency would be the number of waves per second passing a given point. The reciprocal frequency would be the time per wave. The time scale of the absorption process is basically the time per wave. So with light in the visible region, the time scale of the absorption is 10 to the minus 15th seconds. Of course, nano is 10 to the minus 9th, pico is 10 to the minus 12th, 10 to the minus 15th is femtosecond. So light absorption occurs on a femtosecond time scale. Solvent relaxation, it says, occurs on to the 10 to the negative 10th time scale. So interestingly, this is 5 orders of magnitude slower than the absorption time scale, it is still, right, this is a tenth of a nanosecond. And this is really the time period during which solvent relaxation will be completed. Solvent relaxation will be complete after about 0.1 nanoseconds. Fluorescence emission, it's not shown here explicitly, but fluorescent emission typically happens on the time scale of nanoseconds. Typical fluorescence lifetimes are between, let's say 0.5 and 20 nanoseconds. So that's one of the interesting things about fluorescence. Although solvent relaxes more rapidly than fluorescence, and that's important. That solvent relaxation is part of what gives us the Stokes shift. What gives us an environmental dependency in the Stokes shift. We're going to come to that momentarily. And so that's quite an important qualitative feature of fluorescence. But macromolecules, of course, rotate much more slowly than solvent. And so macromolecules rotate on the time scale of the fluorescence. So the time scales are quite important. The time scale of the fluorescent decay is not shown here, but again, it is on the order of, let's say somewhere between 0.5 and in the extreme case, let's say 50 nanoseconds. So basically, fluorescence is occurring on the time scale of rotation of macromolecules. It is occurring more slowly than the time scale of rotation of the solvent. That means the solvent relaxation can influence the energy of the fluorescence emission, the so-called Stokes shift. And then the molecule is rotating roughly on the time scale of the fluorescence emission process. That's extremely useful. That's what we will exploit when we look at fluorescence anisotropy. Fluorescence resonance energy transfer is we'll talk about that in detail. It's basically the transfer of the energy. It transfers the energy of the electronic excitation from one molecule to another. You can think of it as transferring fluorescence from one molecule to another, and that's not exactly what's happening. It's also true the fluorescence acceptor does, the molecule accepting the energy does not have to be fluorescent. It just has to have an absorption that matches in energy the energy of the fluorescence emission. Anyway, we'll come back to that in more detail in a bit, but the bottom line is this FRET process is another way to remove the electronic excitation via a non-fluorescent mechanism. And so FRET will effectively compete with fluorescence, just like thermal de-excitation or so-called non-radiative decay competes with fluorescence, just as collisional quenching competes with fluorescence. All right, so that's an overview of the Jablonski diagram and an overview of fluorescence. Actually, we have already covered all of the most essential sort of physical effects. At this point, you actually, have almost all that you will need to know for the in-class part of the final exam, because that's really focusing on rather qualitative things. We've already covered almost all of the key qualitative points. I guess there are a few qualitative points about anisotropy that we need to cover. But before we go on to anisotropy, I am going to dig a bit more deeply into the effects shown here in this Jablonski diagram, because they are important effects. So we're not going to dwell at them at great length, but I do want to emphasize them and clarify them a bit more, and we'll do that next. Okay, so as I've told you repeatedly, my PowerPoint slides are organized as effectively review sheets. And so these are set up to make it clear to you what the important points are that I want you to remember and take away from the class. And of course, those are the ones that I'm going to query, focus on primarily on the test, probably exclusively focus on the test. So what I'm going to do now is step through these review sheets point by point, and then just refer back to the relevant, as I go through them, refer to the Jablonski diagram and how they illustrate these points. Okay, so key points. And all of this was in Lackowitz, so you should have already have heard it. I think that the descriptions there are pretty good. I think the thing that is missing in Lackowitz is really sort of, the description of what the dipole moment is, and that's why we spent our class time on the dipole moment, because you can't really understand much about what's going on here without understanding that and understanding the vibrational manifold. Lackowitz does not explain that at all, so I emphasized in class spending time on that, because Lackowitz, I think, does explain all of this stuff pretty well. But I will, let's just review the important points. So Boltzmann weights put almost all molecules in the electronic and vibrational, in the ground electronic and vibrational states at room temperature. So what's that saying is that at thermal equilibrium, at room temperature, at biological temperatures, The Boltzmann weighting is such that there's very little occupancy of any of the excited states. And so let's just look one moment in the next slide at the Boltzmann weighting term, right? The Boltzmann weighting says that at thermal equilibrium, the probability of finding a system in a quantum state m compared to n is given by e to the negative delta e. It's going to be inversely proportional to the exponent it's going to be inversely proportional to e to the power of the energy difference divided by kBt, right? So this Boltzmann weighting factor means that at thermal equilibrium, as you go to higher energy states, there will be exponentially less occupancy of them. And even in vibrational states, even for vibrational states which have more closely separated energies, right? Vibrational absorbances occur in the infrared region of the spectrum. The energy difference between vibrational quantum states, therefore, is smaller than that between electronic quantum states, which are generally in the visible or ultraviolet region of the spectrum. And so the vibrational energy states have smaller energy separations between them. But even those energy separations are large enough that the overwhelming majority of molecules will be in the vibrational ground state, according to the Boltzmann weighting. The Boltzmann weighting, of course, is something very similar to what we saw for the weighting of the the concentration ratios at a chemical equilibrium also have a Boltzmann weighting-like term depending on the free energy. When we get down to the atomic and molecular level, instead of, if we're looking at individual molecules, basically R is Kb on the molar level. So it's really the same kind of energetic weighting. This is saying that with the dissociation constant, we were looking at reactants over product, but it is saying, effectively that there is the ratio of product to reactant depends inversely on the exponent of the energy difference between them. The probability of finding a molecule in an ensemble in a higher energy state depends inversely on the exponential of the energy difference between them divided by kBt, right? So let's get back to the Jablonski diagram. The bottom line is that Boltzmann weighting implies that at thermal equilibrium, the vast majority of molecules will be in the vibrational ground state and in the electronic ground state. That's why eventually fluorescence emission or other decay processes will tend to bring these molecules back down to the ground state. At biological temperatures, there's these, even the vibrational energies are large enough that you will have very little occupancy of the vibrational excited state. In the electronic excited energies are even larger, so you even have less occupancy of that. So at thermal equilibrium, everything's going down, right? And so that's an important point. We're going to be generally in the lowest energy quantum states at thermal equilibrium. There can be some, in a large ensemble, there will be some occupancy of the higher energy states, but it is a very small fraction at thermal equilibrium. And so the Boltzmann weighting tells you that. So, important points. Selection rules. So we've stepped through that. I'm going to step through all these bullet points and refer them back to what's going on here, right? So the first bullet point, Boltzmann weights put almost all molecules in the ground, electronic, and vibrational states at ambient temperatures. That means stuff is going to tend to be here. And when you're in the electronic excited state, it's going to tend to be here in the ground vibrational state. And actually higher order electronic excited states will also tend to decay for various reasons. Well, because this energy separation is smaller than this energy separation, it is easier to shake this off by thermal interactions, by collisions in the solvent. And so actually the higher energy electronic excited states also tend to decay without fluorescent emission by internal conversion to the lower energy electronic excited states. So let's step through the rest of these points in detail. So quantum mechanical selection rules, and we've talked about, to some extent the qualitative origin of these things. They allow one photon to induce a transition into a manifold, right, of higher vibrational quantum states in the higher electronic excited state, right? So you can go from, one photon can induce a change from between two different electronic states and between two different vibrational quantum states. And therefore you have fine, right, the vibrational quantum states are more closely separated in energy. You have a fine structure in this vibrational manifold, as it's called, in the electronic excited states. The electronic transition occurs on the femtosecond time scale, which is equivalent to the single period of the light wave. Now, a point that is not exactly schematized here, but I'll touch on, Lacowitz, I believe, if I remember correctly, does touch on this. The electronic excitation energy is lowered and absorption wavelength is increased if the solvent is highly polarizable on the femtosecond time scale. So let's just look at this down here now. So what is this saying? So solvent relaxation that involves actually movement of the dipoles, right? The rearrangement, the spatial reorientation of solvent molecules happens, on a, let's say, roughly 10 to the minus 10th, roughly 0.1 nanosecond time scale. The electronic absorption occurs on this 10 to the negative 15 second time scale. So solvent reorganization is much slower. Orientational reorganization of the solvent is much slower. So basically the system cannot feel or be energetically influenced by the spatial reorientation of the solvent during the time of the absorption, so it doesn't feel that. On the other hand, electronic polarizability of the solvent that does not involve reorientation, right? Like some molecules are just very polarizable. They're electron clouds. So we saw this with the van der Waals forces. And the larger the atom is, the greater the degree of polarizability. Aromatic rings have a greater degree of electronic polarizability. Electrons in atoms can move around on this time scale. And so if there is polarizability on this femtosecond time scale, it actually can affect the energy of the transition, right? If this, to the extent that the solvent has polarizable electrons, the electrons will be able to actually move around and respond to the change in the molecular dipole moment on this time scale. And so basically, the component of solvent polarity that comes from electron polarizability is basically on this time scale. And so that electron polarizability component of solvent polarity will affect the electronic excited state on this 10 to the minus 15 second time scale. And what that means is that so-called fast dielectric constant. The contribution to solvent polarity that comes from, again, electron polarizability can respond to the changing dipole moment on this time scale, and therefore it can lower the energy of the first electronic excited state on the time scale that the light absorption is taking place. If the, right, so basically that means that during the time that the electric field is inducing this change in electronic quantum state. And that, of course, has to change the electronic dipole moment because otherwise light would not be absorbed. Change in to the extent that the solvent can respond to that change in dipole moment on the femtosecond time scale, which will be the case if for the component of solvent polarity coming from electron polarization. That electron polarization component of the polarity or of the dielectric constant, again, can be manifest on this time scale. So on that time scale, polarizability or dielectric constant on that time scale actually will lower the energy of the electronic excited state basically during the course of the electronic transition, and therefore the energy of the electronic transition can change. Now this is a second order effect compared to the solvent reorganization effect, at least for polar solvents like water. Water actually has very low fast dielectric time scale polarizability. Has very low fast dielectric constant. Water has very low electron polarizability. But on the other hand, if you were, for instance, in an organic solvent like benzene, benzene actually has rather high fast dielectric constant, right? Its electrons are really the electrons can move around a lot on the femtosecond time scale, and therefore you can actually get changes in absorption energy in some solvents because the electrons can rearrange and can compensate for the change in dipole moment on this time scale. So that is a somewhat subtler point, but it is important to know because you will see that absorption energies, the absorption spectrum will change in different solvents. That's explained by the change in the relative separation. It's a change in the separation between the electronic and the excited it reflects a change in the energy separation between the electronic ground state and the electronic excited state due to the ability of the solvent to compensate for the higher dipole moment in the excited state, and to do that on the same time scale as the absorption process. Okay, hopefully that makes some sense. Okay, so next point. The heat transfer to solvent on a picosecond time scale causes internal conversion, which lowers the molecule to the ground vibrational state in the excited electronic state, causing the Stokes shift. It's the major contributor to the Stokes shift between absorption and emission. The Stokes shift refers to the difference between the absorption frequency of light and the emission frequency of light. That is called the Stokes shifts. The internal conversion is basically shaking off the internal conversion is shaking off the vibrational excitation, right? So internal conversion means the decline in the vibrational quantum state. So basically, molecules that are still in the first electronic excited state, that are in higher vibrational quantum states, they will decay down to the vibrational ground state. So these vibrational states throw off their energy very much more efficiently via heat, right? The energy of thermal motion is more closely matched to the energy of these differences between the vibrational quantum states. The vibrational quantum states, therefore, on a picosecond time scale, right? So 10 to the minus 12. Absorption process, 10 to the minus 15th femtosecond. Internal conversion, shaking off the energy from the vibrational excited states, that will be on a picosecond, or 10 to the minus 12 time scale. So on this picosecond time scale, things decay from the vibrational excited states to the vibrational ground state. Then when the subsequent emission, right up here, we see also the internal conversion process. This is schematizing internal conversion, both the vibrational internal conversion the vibrational internal conversion would be from there to there, from there to there, right? The vibrational internal conversion will bring it to the vibrational ground state. The higher order electronic excited states also tend to have smaller energy gaps between them than the ground state compared to the first electronic excited state. And so internal conversion, basically thermal motion, can also take away the energy of the electron. They will take away the energy of the electron. The thermal motion more easily removes this energy difference between the second electronic excited state and the first electronic excited state, and so that basically, again, thermal dissipation of the excitation energy, internal conversion, can happen between the higher order electronic excited states. And so what this means is that these, basically, the excitation will be thermally dissipated, will be converted to thermal energy motion in the solvent, again, on a picosecond time scale, such that all of these different electronic excited, all of these different excited molecular quantum states will tend to decay down into the lowest energy electronic excited state in the lowest energy vibrational state, right? So the extra vibrational excitation tends to be shaken off down to the vibrational ground state. Also, extra electronic excitation above the first electronic excited state will tend to be shaken off. Again, just go into the heat of the solvent, right? And then the fluorescence process, and then the relative rate scales become quite important, because that process occurs on the picosecond time scale. Fluorescence will occur after, which occurs on the nanosecond time scale, will occur after the internal conversion process. And so for that reason, the energy of the fluorescence emission is lower. The wavelength, right, the energy of the fluorescence emission is lower. Sorry, the energy of the fluorescence emission is lower than the energy of the absorption, right? The fluorescence emission will occur from a lower energy state than the absorption brought the molecule to, in general, because of the internal conversion process, and that's what causes the Stokes shift. The fact that fluorescence is generally at lower energy, higher wavelength than absorption. Okay, so that's another important point. Now, solvent relaxation reflecting polarizability on the picosecond nanosecond time scale. This is what's called the slow dielectric constant. This reflects the polarizability of the solvent due to rotational reorientation of dipoles, right? So electron polarizability occurs Electrons can be polarized on the femtosecond time scale and can influence even the absorption process. Dipolar relaxation, reorientation of the solvent, takes place on the roughly 0.1 nanosecond time scale. And so that solvent reorganization occurs more slowly than the absorption, but it will occur more rapidly than the fluorescence emission. And so the energetic stabilization of the electronic excited state by solvent reorganization will be reflected in a decreased energy of the fluorescence emission. So solvent relaxation lowers the energy of the first electronic excited state on the 0.1 roughly nanosecond time scale. Therefore, that lowers the energy of the system prior to the fluorescence emission. And so that solvent relaxation effect will influence the Stokes shift, right? The Stokes shift is between the energy of the initial absorption compared to the energy of the fluorescent emission. Internal conversion produces some Stokes shift. Solvent relaxation produces further Stokes shift. More polarizable solvents, well, solvents with more dipolar polarizability, right? Electronic polarizability will affect the absorption. Dipolar polarizability will increase the Stokes shift. And so this is one very powerful property of fluorescence for molecular studies. It's actually sensitive to the solvent environment. The fluorescence, the magnitude of the Stokes shift will depend on the ability of the solvent dipoles to reorganize themselves to lower the energy of the first excited state, right? Remember, for electronic absorption to take place, driven by the electric field of light, this dipole moment has to change compared to that one. When the dipole moment changes, the solvent dipoles will want to interact with it differently. They will therefore reorient to basically compensate. If it's a higher dipole moment, they will reorient to shield that dipole moment more. That will lower the energy of the first excited state. That solvent relaxation effect, therefore, will be an additional contribution to the Stokes shift. In a solvent that has a lot of dipolar polarizability, you will see an additional Stokes shift. So what does this mean? That means that the energy, the frequency and the energy of the fluorescence emission is environment dependent. It depends on the solvent properties, and the Stokes shift is strongly influenced by the dipole moment of the solvent and then the rotational diffusion rate of the solvent. Water has a lot of dipole moments, and water molecules diffuse rather rapidly. Water has again a lot of dipolar polarizability. There's a strong dipolar contribution to the dielectric constant. This is the so-called slow dielectric constant. It's called the slow dielectric constant because it happens on, again, the 0.1 nanosecond time scale compared to the fast dielectric constant that comes from electron polarizability, electron movement within molecular orbitals that occurs on the femtosecond time scale. This slow polarizability will influence the Stokes shift, right? It will involve a lowering of the energy of interaction of the solvent with the excited state of the molecule on a time scale much slower than the excitation time scale, but much slower than the excitation's time scale, but significantly faster than the time scale of the fluorescence emission. And so the solvent relaxation will be reflected in a lower energy of fluorescence emission. So in a polar solvent like water, you will see fluorescence emissions at a lower energy, higher wavelength than you do in an apolar environment. And this is ultimately the source of the environmental sensitivity of the Stokes shift. So that's quite an important point. Next, fluorescence quantum yield depends on kinetic competition in this so we're now basically internal conversion, just thermal dissipation of the quantum mechanical excitations will lower the system to the ground vibrational state in the first electronic excited state. Solvent relaxation subsequently might lower the energy of that first electronic excited state even more, and then you will get a fluorescent emission on the nanosecond time scale. But several other non-fluorescent processes will compete with that on the nanosecond time scale, including, although it's harder for thermal energy to remove that much energy from the system, right? Because this is now a greater magnitude of energy. The difference in the electronic The energy difference between these two quantum states is greater than that between the other quantum states that we looked at, between the vibrational quantum states and between the different excited electronic quantum states. So thermal energy removes that excitation less efficiently, but it can still remove some of it. And so that kind of, they're called non-radiative decay pathways. Again, it's basically solvent molecules bumping into the excited state molecule and removing the energy of the excitation by having it transferred to the kinetic motion of the solvent. So those that kind of non-radiative decay, again, sort of thermal dissipation of the excitation energy, will compete with fluorescence. Collisional quenching involves very specific kind of pathway removing electronic excitation more efficiently. This can also occur on the nanosecond timescale. It will be collisional quenching will depend on the concentration of a quencher. We'll come back to that shortly. That's another competing process. Fluorescence resonance energy transfer, basically a dipole-dipole interaction between one fluorescent species and one absorptive species. The fluorescence resonance energy transfer can transfer the excitation from one fluorophore to another fluorophore or chromophore. That will also compete with fluorescence. When you have a FRET, fluorescence resonance energy transfer, the excitation can move from a so-called donor fluorophore to an acceptor fluorophore. And that acceptor fluorophore can then fluoresce. That's an incredibly useful property that is exploited widely in many different kinds of experiments, including experiments that you saw in papers covered in the course of the semester. But it's not shown here, but I will point out that fluorescent decay from the acceptor will also be competing with the collisional quenching, possibly in the thermal relaxation of the excitation in the acceptor. So even though once the resonance energy transfer once the resonance energy transfer process has moved the excitation energy from one molecule to another, the fluorescent property process in that molecule will compete with all of these same things. And in some molecules, these other processes can greatly dominate the rate of the fluorescent decay, and that means in the end the molecule is minimally or non-fluorescent. And so non-fluorescent molecules can undergo resonance energy transfer, but then if they are not themselves fluorescent because of the competition from these alternative decay pathways, you will not get any fluorescence at all. All right. So again, fluorescence quantum yield will depend on the relative rate of this. So it's now going to be a kinetic competition. We're going to have a kinetic competition for the removal of energy from the first electronic excited state down to the ground state. And so the fluorescent emission process, the process of firing out a photon of the right energy, will compete with these other decay processes. In that kinetic competition, we'll describe the relative amount of fluorescent compared to to all sorts of other kinds of decay, and that is what is going to be defined as the quantum yield. And so we'll come back to that in a bit. But the bottom line is fluorescence quantum yield depends on kinetic competition in the first electronic excited state between photon emission and various quenching processes that return the molecule to the electronic ground state without emission. So selection rules allow one photon emission to return the molecule. So now we're down here. Selection rules, quantum mechanically, these are actually exactly the same and symmetrical with the selection rules describing the excitation. And so for that reason, one photon emission can return the molecule to a manifold of higher vibrational quantum states in the ground electronic state, right? So for the same reason that the absorbed photon could bring the molecule into a manifold of higher vibrational states, the emitted photon can bring the molecule into a manifold of higher vibrational states. There is not an equal probability of decaying into each one of them. In generally, the probability is highest of decaying all the way to the ground state. But because of the symmetry, the quantum mechanical symmetry in the absorption and the decay processes, you will get the mirror image appearance, rough mirror image appearance of the fluorescence emission and absorption. Okay, so that accounts for the mirror image rule shown in the previous slide. Now, one final phenomenon that can be schematized in the Blonsky diagram is phosphorescence, What is phosphorescence? Well, phosphorescence is really physically the same process as fluorescence, but it occurs on a much slower time scale. Why does it occur on a much slower time scale? Well, what happens here is that this has to do with electron spin, right? In the electronic ground state, right, you will have paired electrons with opposite spins. The electronic excitation process will take one of those one of those electrons, and put one of those electrons into an excited state orbital. That process, when driven by the electric field of light, will preserve the spin of the electron. So during the electronic absorption process, the spin does not change. However, now that it is now that it is alone, one electron alone in the first electronic excited state, the Pauli principle no longer prevents that from right down here. The Pauli principle, every particle has to have a unique quantum number. The spins have to be paired. You cannot have two up spins in one electron. It violates the Pauli principle. In the first excited state, however, now you have one electron in the orbital and it can flip. And so intersystem crossing reflects that flip in electron spin. Once you get to the excited state, with some probability, the electron spin can flip. When the electron spin flips, this electron can no longer rapidly decay to the electronic ground state. Why? If this electron were to go right, so this is the we're going to say in this case the electron that was promoted had up spin. If it changes to down spin in the electronic excited state, if this now were to decay to the electronic ground state, you would have two down spin electrons. That is forbidden by the Pauli principle, and so it basically doesn't happen. It means that for the energy to be shaken off in the form of a emission of a photon from this so-called triplet state, this is called a triplet state because of the unpairing. The history of this, the etymology of this is a little bit complicated. It comes from electrospectroscopy, but in any event, the state with an unpaired electron right here, all the spins are exactly canceling each other out. Here, basically, you end up with net spin. When you have net spin, it's called a triplet state. For this electron to decay to the ground state, it has to simultaneously flip its spin and change its electronic quantum state. That is a so-called quantum mechanically forbidden process. Doesn't mean it never occurs, it just means it occurs much more slowly. And so phosphorescence is basically a fluorescence-like phenomenon, but on a much slower time scale, because the spin flip of the electron greatly kinetically retards the process or the probability of decaying to the electronic ground state. So the Jablonski diagram can also be used to describe the phosphorescence process. The term intersystem crossing is referred to that spin flip phenomenon. So the Jablonski diagram, one form of the Jablonski diagram can capture that phenomenon, can provide an explanation for that phenomenon as well. All right, so let's move on. So we've really sort of covered this, and I'm going to go through this pretty quickly, so I'm just going to read this and then refer back to the Jablonski diagram. So as I said before, the Stokes, this point was made on the previous slide, but let's just clarify it a bit. The Stokes shift in photon energy is influenced by solvent relaxation between absorption and emission, right? So so the absorption process will happen into a excited electronic and possibly vibrational state, but internal conversion will rapidly reduce all of those things to the vibrational ground state, and that'll all happen on a picosecond time scale, right? Absorption femtosecond time scale, internal conversion to the lowest vibrational quantum state, picosecond time scale, solvent relaxation, slower than the picosecond time scale, but let's say roughly 1/10 of a nanosecond time scale. And so this solvent relaxation process then will affect the energy of the excited state, right? So how does this work? So the solvent around a fluorophore will shield it electrostatically to minimize Gibbs free energy, right? So in well, certainly there has to be a change in dipole moment, key point why we spend a lot of time on dipoles. There has to be a change in dipole moment for an electronic absorption to take place, driven by the electric field of light. But in the ground state, there probably is going to be most molecules will have some dipole moment. the solvent will equilibrate to reduce the energy of interaction, right? The solvent will reorganize itself to minimize the interaction energy. Of course, thermal motion will keep the solvent moving to an extent, so you'll have a balance between thermal motion and reduction in the electrostatic interaction energy. But as we've seen in at other points in the course, the solvent dipole moments will reorient themselves to, again, shield the molecular dipole moment in the fluorophore. And so that will achieve a thermodynamically controlled balance between the electrostatic energy of solvent molecule interaction and the thermal motion of the solvent. So that will be basically in some kind of equilibrium state of shielding. Now, when you increase in the course of the absorption, the dipole moment has to change. What's schematized here is an increase in dipole moment. When that dipole moment increases, basically, there will no longer be an optimal energetic interaction between the solvent and the molecular dipole. With the larger molecular dipole, right, the solvent, if it's a larger molecular dipole moment, and you're in a solvent like water, which is a dipolar species, basically there will be a tendency to get more reorientation of the water dipoles to produce more shielding. The greater shielding will lower will lower the energy of that electronic excited state. And then that solvent relaxation process, again, occurs on a slower time scale even than the internal conversion. So it will not influence the dipolar relaxation of the solvent, right? The reorientation of the solvent dipoles occurs on a roughly 0.1 nanosecond time scale. That process will be subsequent to the absorption, so it will not affect the absorption. It means there will be yet a further reduction in the energy of the first excited state, and therefore a reduction in the energy of the emitted photon due to this solvent relaxation effect. So this interaction depends on the molecular dipole moment, which must change during an electronic transition driven by light absorption. Therefore, solvent relaxation after absorption lowers the energy of the excited fluorophore solvent system in the vibrational ground state, further reducing the energy and frequency, increasing the wavelength of the emitted photon, right? So more polar solvents generally produce larger red shifts, right? More polar solvent, more energetic stabilization of the electronic ground state, lower energy photon, higher wavelength photon. Higher wavelength is going towards the red end of the visible spectrum, so this produces a so-called red shift, a greater reduction in emission. So polar solvents produce a greater reduction in emission frequency compared to excitation energy because they generally shield dipoles more strongly. This is the origin of the solvent dependence, the Stokes shift. More polar solvents have more solvents that are more polar due to their dipoles give greater Stokes shifts. And there's this, in the end, this is exploited in many biophysical experiments. It's quite a convenient property that there is an environmental sensitivity to the Stokes shift. Okay, so now just to this, then we'll emphasize this, and this sort of repeats and clarifies another point from the previous slide. However, it is important to note that the Stokes shift depends critically on the physical mechanism underlying solvent polarity. It is strong when solvent polarity arises from reorientation of molecular dipoles, right? The Stokes shift is strong when when the polarity is when the polar interactions of the solvent come from reorientation of molecular dipoles. It's strong because this process occurs on a picosecond to nanosecond time scale and is slower than photon absorption, which occurs on a femtosecond time scale, right? So to get a Stokes shift, you need a change in the molecular energy state between the time of promotion to the electronic excited state and the time of emission of the photon. Dipolar relaxation of the solvent occurs on that time scale and produces large Stokes shift. In contrast, polarizable electron clouds respond to electrostatic perturbations much more rapidly. To the extent that the solvent has polarizable electrons, those actually can respond to the change in dipole moment on that femtosecond time scale. So, in contrast, polarizable electron clouds respond to electrostatic perturbations much more rapidly, even as fast as the photon absorption process, which reduces both excitation and emission energies equally, right? If the solvent can respond on this time scale, the electronic excited state is stabilized, even as it is initially formed during the promotion of the electron to the electron excited state, right? So if the solvent can respond to the electric dipole in the molecule on the time scale of the absorption, already by the time the photon is absorbed, one way to think of it, by the time the photon is absorbed, this molecule is already having more favorable energetic interactions with the solvent, and therefore the energy of the state is reduced slightly, and therefore actually the absorption energy is reduced. Okay, so therefore the spoke shift is smaller when electron polarizability makes a strong contribution to solvent polarity. Why? Because the polarity effect has already influenced the absorption energy. If the polarity effect influences the absorption energy, you will not see it in the Stokes shift because it has already, influenced the absorption energy. So, and it turns out that measurement of the dielectric constant, reflects the speed of light in a given medium, but it is dependent on the polarizability of the solvent. So measuring the dielectric constant on different time scales, for light versus, let's say, static charge. The dielectric constant will, slight oversimplification, sorry. The dielectric constant has contributions from polarizability, electron polarizability, and from dipolar rearrangement. The dielectric, the so-called fast dielectric constant will reflect, will influence actually the speed of light, right? Because light, to the extent that the molecular environment can interact with the electric and magnetic fields of light on the time scale of their oscillation, that actually will influence the propagation of the light, right? And so that contribution of the dielectric constant that influences the properties of the light wave that occurs on the femtosecond time scale, that is actually, that influences the refractive index. The refractive index of a medium reflects again, sort of the refractive index reflects the electrostatic response of the medium to the oscillation of the light. It reflects basically the ability of the electrons in the medium to move around on the frequency scale of light in order to interact with the electric and magnetic components of the light. And so basically, these sort of end up factoring into the Maxwell's equations relationships that determine describe the propagation of light and describe the velocity of light. So these electronic polarizability on the femtosecond timescale actually influences the refractive index, which is a measurement of the speed of light. And so those fast timescale polarizability actually can be quantified via the refractive index. The dielectric constant will contain contributions both from that fast timescale polarizability that's reflected in the refractive index, and also from the slower timescale polarizability reflected by the dipolar rearrangement. And actually, this stuff can be measured by comparing the dielectric, by looking at the refractive index of light, and then by looking actually at the dielectric constant on different timescales. You can sort of sort out all these properties. That is a rather extensive, rich, and elegant area of physical chemical research. We won't go into it in detail, but you should know that it's there and have an idea of why it's there. That's the goal of this. Now, again, so what this is supposed to show again is that this differential Stokes shift depends on the solvent polarity, but specifically the differential Stokes shift. The differential Stokes shift in different solvent environments depends on the dipolar contribution to the solvent polarity, because dipole reorientation happens on a timescale between absorption and emission, and so dipolar reorganization produces the environmental dependency of the Stokes shift. Okay, so we've now reviewed that a number of times, perhaps too many times, but this is incredibly important, and do want this to really be clear in your minds. Okay, next point. So I'm not going to go through the math now other than very, very quickly. But again, so an important point now that also is captured in the Jablonski diagram is that the efficiency of fluorescence emission will depend on the relative rates of the fluorescent emission process compared to all the different kinds of processes that remove the excited state energy by ways other than via fluorescence of this molecule that was initially excited. And so in the end, what we're going to say is that the quantum yield reflects the fraction of the excited state molecules that decay via fluorescence via all other processes. This is going to be an important parameter quantitatively for many, many reasons. The quantum yield will be given by the fluorescence emission rate over the rates of all the different energy removing processes. So as schematized here, the quantum yield would be the rate of the fluorescent emission divided by the sum of the rates of fluorescent emission plus thermal de-excitation plus collisional quenching plus resonance energy transfer to any absorptive species that are nearby. And so this kinetic competition will determine the relative fraction of the excitation energy being emitted as fluorescence. That is described as the quantum yield. If you think about this for a while, we'll go into this a little bit more deeply in a bit. But if you think about this, effectively this is a rather complicated kinetic process, and understanding the quantum yield based on, sort of integration of those kinetics would be quite complicated. But you can just, right, but the relative efficiency of the relative amount of fluorescence emission compared to other kinds of de-excitation will just be given by the relative rates. So this is quite a clever thing. You can get the fluorescence quantum yield just by looking at the relative rate of the fluorescence processes compared to all of the decay rates. And so this kinetic competition that you can illustrate in the Jablonski diagram, again, the quantity, the magnitude, the relative rates of these things are not illustrated, at least in this version of the Jablonski diagram. You can make these arrows sort of more thick or less thick to try to capture something about the relative rates. But in any event, that's not done here, and of course it's not quantitative or easily quantifiable in any event. But the important point is that these rate ratios will determine the quantum yield. So if the rate of the fluorescence decay is, let's say, 1/5 of the total rate, that means at any moment in time, 1/5 of the excitation will be going out in fluorescence. And if that's true at any moment in time, right, these processes all just mutually compete with each other for any electron in the excited state. So if at any moment 1/5 of the excitation energy is being released as fluorescence and 4/5 is being released by all other processes combined, that means that overall, in total, 1/5 of the fluorescence, 1/5 of the excitation energy will be emitted as fluorescence. We call that the quantum yield, the fraction of the total excitation energy that is being emitted as fluorescence, the fraction of molecules that make it to the electronic excited state that will emit that energy as fluorescence. And so quantum yield is important for a number of reasons. We will come back to this later in a separate screencast and think more about the math of this situation. Again, the point of this screencast is to just go through the qualitative details. Okay, and so now let's look at collisional quenching. Collisional quenching occurs at a rate proportional to the concentration of a specific molecule in the solution. It's alternatively irritating and useful. It does not require physical contact, but rather involves electrostatic or more likely electrochemical conditions interaction. And so these electrostatic and electrochemical interactions actually depend on proximity. And what they do is they remove the excitation, probably mostly by actually just taking that electron away from that molecule, right? If the electron, right, in the minimal review, in the electronic ground state, you will have paired electrons in the ground state electronic orbital. The excitation process will promote one of those electrons into the electronic excited state. Suppose some other molecule comes along and just grabs this electron away from it. That is effectively something called photo-induced electron dissociation. Right? So photo-induced electron dissociation. Photo-induced electron dissociation happens because a photon has promoted an electron to an excited state. When the electron is in a higher energy state, it's more easy to remove it from the molecule. If another molecule comes along that, let's say, has a hungry electron cloud, or let's say it just has an excited state electron cloud that's roughly at the same excited state. Let's say another molecule comes along that has a electronic quantum state that's roughly at the same energy. that electron rather, can just move to the other molecule that has an empty electron cloud that would, I'm sorry, an empty molecular orbital that would accommodate that electron at roughly that energy level. This process of photo-induced electron dissociation is essentially that. It's having another molecule come along and take the electron away. If the electron is removed from this molecule, it obviously cannot undergo this fluorescent decay. So you've lost the excitation. You've actually lost the electron, but you've also lost the energetic excitation by a non-fluorescent pathway. Collisional quenching is believed to mostly occur through this process. So there are particular kinds of molecular species that will be prone to do this. So guess what one of them is? One of them is oxygen. Molecular oxygen has relatively low-lying, energetically low-lying, unoccupied molecular orbitals. Oxygen will pick up an electron relatively easily. Oxygen is a quencher. Acrylamide, which you may have heard of because it's used to make gels that we use for electrophoresis, it has a vinyl, acrylamide is, in a sense, designed. It is a molecule that we use because it is easy to form covalent carbon-carbon bonds between acrylamide molecules. That's possible because the highest occupied molecular orbitals have relatively high energies, and therefore they readily, when you go into a higher energy molecular orbital, it is more easy for the electron to be removed. Effectively, that's one of the things going on in acrylamide. It has relatively low-lying excited state molecular orbitals, and so it can pick up electrons. It's that ability to pick up electrons that actually helps it polymerize, right? Because it basically, when it polymerizes, it takes an electron from one acrylamide molecule to form a covalent bond. So acrylamide is another quencher. Iodine has a very, very polarizable electronic structure. It also has relatively low-lying, it's a very large atom. It has relatively low-lying unoccupied electronic orbital states. It can pick up an electron. So a polarizable species, species with relatively low-lying electronic molecular orbitals, they can just, if they get close enough, they can just pull the electron away. And that process is probably the main contributor to collisional quenching. Collisional quenching is it removes the excitation energy by a pathway other than fluorescence, and therefore it competes with fluorescence kinetically and reduces quantum yield. Biochemists and biophysicists can manipulate this to very useful effect to study molecular properties. And so that's an interesting and commonly used technique in biophysics. It's also a huge pain in the rear end, practically speaking, because there are lots of quenching species around in the environment. Oxygen is probably, the most annoying of these because oxygen is all around us. And so effectively, if you want to use fluorescence, you often want to get very high quantum yield. Well, ideally, you would have 100% quantum yield. In any process that removes fluorescence, removes excitation energy other than via fluorescence, will lower the quantum yield and lower the amount of fluorescence emission and therefore lower the sensitivity of the experiment. These kinds of quenching species, again, oxygen is around all the time, and in solutions that you're doing experiments in, or for instance, slides that you have fixed on cells that you have fixed on a microscope to do immunofluorescence, these quenchers can be a real problem. They can end up under unfavorable conditions, basically removing most or all of the excitation by non-fluorescent pathways, and so they can reduce the efficiency of they reduce the fluorescence quantum yield, and therefore they reduce the photon emission, and they can basically kill fluorescence experiments. In other contexts, we can use collisional quenching to study molecular properties in a useful way, but in some contexts, it's just a big, again, pain in the rear end. Okay, so that covers that. And here is an interesting paper that shows that most collisional quenching occurs via PED, or photo-induced electron decay. Essentially, well, these authors follow up on a landmark study, as it says, 40 years ago. And so this would be in the early 1970s by authors named Rem and Weller. They showed that the collisional quenching power of solute molecules correlated with the difference in it correlated with the energy level of their unoccupied, of their low energy unoccupied molecular orbitals, and it basically showed as you get a better and better match between the energy level of the unoccupied molecular orbitals in a quenching molecule and the energy of the fluorescent excitation. As that energy gap, as the energy gap in the two molecules is more closely matched, you get much more efficient collisional quenching, and that quantitatively you can actually explain the efficiency of series of different molecules as collisional quenchers based on that energy gap, which then suggests, again, it's actually very strong evidence that collisional quenching is occurring primarily from having the electron extracted from the excited state of the fluorescent molecule and transferred to another molecule. Now let's think about that for a moment. Sorry, back up for a moment. Let's think about that for a moment. So what happens, right? So we start with two electrons, sorry. We start with two electrons paired in, let's say, an orbital in the electronic ground state. One of those electrons is now promoted by a photon to the electronic excited state. And so now, although their spins are still opposite one another, you have let's say, the downspin electron remaining in the lower energy molecular quantum state, the upspin electron now in the higher energy molecular quantum state. Now let's say some other molecule comes along and just pulls this thing away and sucks it off of this molecule. What happens? Well, you are left with a single downspin electron in the electronic ground state. So basically, you have converted this molecule now into a free radical with that is missing one electron that is required to complete its valence structure. As you know, free radicals are generally rather reactive species. What are they going to react with? Well, I can tell you if you have any significant amount of oxygen around, these fluorophores will interact with the oxygen. They will chemically and covalently react with the oxygen. When they react with the oxygen, their molecular structure will change, and therefore their electronic molecular orbitals will change, and therefore their fluorescent properties will change. So this is a process called photobleaching, right? During the fluorescence process, because you promote the electron to a higher energy molecular orbital, it is easier for that electron to be removed. Collisional quenching is probably generally occurring via the removal of that electron. If you're lucky, the electron might sort of come back, right? This process often will make the quencher temporarily put that into a free radical state. If you're lucky, the electron will come back into the ground state here one way or the other, and you will restore the proper chemical structure. But it's just easier for reactions to occur when you promote an electron in a molecule to a higher energy state, and particularly if you remove that entirely and you leave this molecule in a free radical state, it is likely to react. It's going to react relatively rapidly with whatever reactive species are around. And because we live in an oxygen-filled environment and oxygen reacts very rapidly with free radicals, this is a problem in fluorescence spectroscopy. We are often struggling to avoid what's called photobleaching. Again, this process is called photobleaching. Well, there are many. The covalent reaction of a fluorophore with other species in the solvent, due to the fluorescent excitation, it typically will frequently render the molecule non-fluorescent. At that point, we say the molecule is bleached, and so that's called photobleaching because it was the initial photon excitation of the fluorophore that put it into the state where it was more reactive and led to the photobleaching. So that's also an important sort of series of related points. And this is a neat paper that follows up on other really nice physical chemical research that showed how this process happens.